up on the screen right now. Now, in looking at your homework, it's fairly obvious and not unprecedented or unusual that we have some work to do. Okay, because just in looking at some of the problems, 54 for one comes to mind, 25 comes to mind. That what I'm seeing on your paper is missing a lot of stuff. Okay, now, not totally surprising because it's kind of the first time we're seeing these kind of problems, but these problems, like this chart stuff, global max min, this whole thing here, this is a big part of the AP test, a big part of our final, our midterm, a big part of next quiz, which will be Monday. Okay, so we've got a ways to go. Now, it's only Tuesday, so that's the good news. Okay, there were a number of people in here quite early this morning, not very many from this section, but there were quite a few people in getting help. And I would say that will probably, like I told the other class, in looking at the homework papers, it looked like there were some people who put their book in their bag and didn't spend much time or didn't have it out very much after they left class, and that doesn't work very good ever, but it doesn't especially work very good in these things. We're getting into a bunch of algebra stuff, and we're getting into some things. So again, I understand that it's the first time we're getting into this, and and we've got some things to learn. And so if you were on some of them and just didn't know where to go, what to do, like 46 would be an example of that, okay? But so I can understand not having something there. But then again, if there were 2 or 3 or 4 or 5 of them that you really didn't know what to do or you just jotted a few things down, then of course the next thing would be to make sure you're coming in and asking questions and stuff. And if you're not doing that either, then it's kind of like, well, what were you thinking? I mean, So we got a lot to do today. Okay, we got a lot to go over today. Very important day as far as the things we're going to cover and understand going forward, so that hopefully you can have more productive practice time. I mean, as I look at what I'm seeing on some of the paper, and again, I can only see so much just looking at the homework paper. I sense it may not have always been the most productive time if you weren't sure what you were doing and so forth. So it's hard to get good practice. So let's hope so ask questions if things aren't making sense. What I tried to do here was I tried to separate, this would be like problem 19 over here, and this would be like problem 23 over here. Chart stuff. What do I mean by chart stuff? Well, any question that asks for local max min, where a function's increasing or decreasing, where it's concave up, concave down, where it has inflection points. That's chart stuff. Because all those things are things here in the chart. So any question that's asking for these things, that's chart stuff. Okay? Global max min is the greatest and the littlest output of a function. The greatest and littlest output of a function. Now, where in the world would you look for greatest and littlest output? It could be anywhere. Well, it turns out it can't be anywhere. It can only be where? A stationary point, right? A local max or min, right? The largest or smallest values of a function can only be at the endpoints, if there are endpoints, and at a local max or min. That's the only places that the largest and smallest values can be. So those are the only places we have to look. And by look, I mean we need to find what those y values are at those places. So that's what a list of candidates is. We find where our local max and mins are, and I don't even care if they're local max and mins, let's just call them stationary points, right? I just find where the derivative is 0, and I got my endpoints, and I take those and I plug them into the function. So what I tried to do is I said, we could take a problem, an f function, that would be the same exact f function, and we could be asked to do this problem, or we could ask to do this problem. Okay, it just depends. Or we could be asked to do both, actually. Now, the squiggly line I drew across here is saying that here's our function f. In chapter 1, we dealt with graphs, and I felt like we knew the chart pretty well. That quiz went pretty well on the chart. But now all of a sudden I feel like we don't know it. It's almost like we did a great job studying for that quiz, and now we don't know it very good. So you've got to get into the chart, and you've got to know the chart. I mean, those things in there just got to be automatic. So that's a goal for you over the next couple of days. You've got to know the chart. Okay? If you have to always be looking back and forth at it all the time, that makes it tough. Okay? But in chapter 1, we dealt with graphs. I think graphs are the easiest way to deal with these functions because it's visual. You can just see. You can see when it's positive. You see when it's negative. You see when it's going up, going down. You see local maxes. You see inflection points. But we're not dealing with graphs now. We're dealing with equations. So when we talk about these today, we got to pretend we can't see this picture. All we have is an equation for f. Right? So pretend I can't even see this picture. So if I've got an equation for f and I want to know where its local max and min are and all that stuff, what do? Well, it all has to do with the derivative. All the important points of this function I've labeled. Now to make it easy, I've called them 1 through 7. So if it's a chart stuff problem, the first thing we do is do the derivative with our new rules that we got, right? Our power rule, right? Bring the power down front, blah, blah, blah. We do the derivative. We set it equal to 0. Why do we set it equal to 0? Right? Some of our important points are where the slope is 0, right? So we want to know where the slope is 0. So we do that first. Well, in this case, it's at 2, 4, and 6. So we talked about making a number line, right? So we make a number line and we put 2, 4, and 6, and that's where f prime is 0. And then how do I get that f prime is positive? How do I get that? I plugged in. Didn't look at this. Remember, we can't see this picture, right? All we have is an equation. I plugged in like a 1. Into what equation? F prime. Because I want to know where f prime is positive. It goes back to the chart. Where f prime is positive, what's this graph doing? Going up. This graph's going up here. And then f prime is negative. That tells me it's going down until 4. And then it's f prime is positive here. It tells me f's going up. Right? So that, and so what do I know is happening at 2? What do I got at 2? Local max. Why? Because f prime is going from positive to negative, so f is going from increasing to decreasing. So I got a local max, I know that's a local min, I know that's a local max. I got a lot of information right there in that number line, right? Now, yeah, if I can see the graph, sure, up, down, right? But I can't see the graph in these problems we're doing, right? We just have an equation for f. This number line tells me everything I need to see as far as increasing, decreasing, and local max, local min, right? So if I go to the chart, all this stuff right here, I get off of that number line right there. Number line is 0, plus, and minus. It tells me all that about this. Now, how can I find out this stuff about f? Go down here to the second derivative and do a number line for that. So I do the second derivative. Do what with that second derivative? What do you mean, same thing? Set it equal to 0, because what I want to know is where it's concave up and concave down. I want to know where the second derivative is positive or negative. Well, if you want to know if something's positive or negative, first find when it's 0, right? Because if it's going to switch from being positive to negative, it's got to do it at 0. So if you want to know if something's positive or negative, if a function's positive or negative, first find out if the function is 0. So I'm going to do the second derivative set equals 0. It turns out that's at 3 and 5. Then I'm going to pick numbers in between. Why? To see if it's positive or negative there. I know where it's 0, so everywhere else it's got to be positive. Does that make sense? If I know where it's 0, everywhere else it has to be positive or negative. Right? So it's 0 at 3 and 5, so everywhere else it's got to either be positive or negative. So I plug in a 2, plug in a 4, plug in a 6, whatever, and I got these values. So what's that mean right here, that f double prime is negative? Remember, you can't see this. F double prime is negative means f's concave down, right? That's in chart, got to be automatic. F double prime is negative means concave down, sure enough, right till there. Then it's concave up. Then it's concave down. What's that mean 3 is? Flexion point, 5. Flexion point. So, because f double prime changed from negative to positive, this changed concavity, so that's inflection point. Same thing there. That's chart equation. That's everything. So right there, those two number lines tell me everything that's in the chart about f. Everything. And I got it by doing f prime equals 0 and f double prime equals 0, right? Okay, now they give me a problem where now I don't want to know when this graph's going up and down. I don't want to know where its local maxes and mins are. I don't care about its inflection points. I just want to know what's the greatest value of this, I mean output. Where's the greatest output of this and the smallest output of this? Well, it could be anywhere. No, it couldn't be anywhere. It can only be where? In points or where the derivative is 0. So I start out the same way. I do the derivative, set it equal to 0. It turned out that's at 2, 4, and 6. I call those candidates. I might have a largest value or a littlest value at 2, 4, or 6. How do I tell? I plug it back into the original function, see what its output is. My endpoints are 1 and 7, so I plug those in as well. So if I had an equation, which I don't have, so I left it blank, but if I had an equation instead of this, I would plug in a 1, a 2, a 4, a 6, and a 7. I would get outputs, and sure enough, I would find that my biggest output would be here at 2. That'd be my max output. And my min output would be down here at 7. Right? There you go. Hopefully that helps. I'll save this as a PDF and I'll put it up on the website. Okay? Now, questions on the homework. Throw some out at me and I'll see which ones we can do. I know which ones I want to do and we'll see if there's any. 54. 44. 46. 25. Okay, let's stop there. Now, 46 we're going to skip for right now. We may get a chance to get that tomorrow. That's the least important of those that we have. Let's do 25 first. Let's see. Our viewing audience at home is not going to get a seat. All right, what did I say we were going to do first? 25? Is that what I said? Okay, 25 says f of x is what? Okay, Richard? We're going to be charged this. Okay, now, all you have to do. Okay, yeah. Okay, all you're going to have to do is you're going to switch, see this purple thing right here? You got to pay attention. You up for it? See these two pages right? Because if you don't, then we're going to write it. Right. You're just going to go back and forth between these two pages. Okay. Okay. So when I tell you, so you don't have to hang on to it. You can set it aside so you can write stuff down. Unless you don't want to write it. Just when I say switch. All right. So what do we got? F of x equals what? That right there? That's what you said, right? Right. Because I know in this section, for this next quiz, almost every problem we do somehow is going to involve doing a derivative. Almost every single problem is going to involve doing a derivative, right? Unless it's some kind of true, false, or some conceptual kind of question or something. But we're going to be doing derivatives. And we're going to be learning rules for derivatives. We already got our shortcut rule. We already know about kicking out of 2. We know about, e to the x is its own derivative. We know the derivative of sine is what? Cosine, right? And we already know some derivative rules. We're going to expand those a little bit today, but we're going to be doing derivatives, all right? And so since I know I'm going to be doing derivatives, I want to written this pattern, okay? Now, it might help that I also remember that this was written this way because this is switch. This is which of these two kinds? There you go. Which of these two types of problems are we doing here on 25? Global max min, right? Second one. And I know that I'm going to have to plug some numbers into that original function. And so it would be easier to plug them in if it looked like this than if it looked like this. Okay, so I'll kind of keep in mind that it was this, but that's what I'm doing. Okay, switch back. All right, so what am I going to do? Zeros of derivative. So I'm going to do f prime equals 1/2 1 half x to the negative half plus 3 x to the negative second. And equals 0. You just got a point. Good job. You have 1 point for getting that done properly and say equals 0. If you don't have the equal 0, you don't get the point. Okay? Yeah. 1 point on this question on the quiz out of 35 or how many. Okay? So there's a point. All right? And that's how these, and that's another big thing about how I'm doing these, and that's when I say when I looked at your homework, there was a lot lacking in what I was saying. Well, part of that is we haven't went through the process enough, and you practice, and I haven't emphasized it. Hey, this is how it's got to look, and so forth. That's part of what we're going to be doing over the next several days. Okay. So you have that on your paper. You get a point for doing that. That's how these kind of problems are graded. That's how they're graded on the AP test. That's how I grade them. Okay. You got a point for doing that. Okay. If this was a calculator question, you'd do exactly the same thing. Now, could you have the calculator do the derivative for you? Yes. You could. Now, to be honest, on one like that, I would hope it would take you longer to type it in than it would to just do it by hand. Hopefully, you would just be a lot easier to just do it by hand most time anyway. But you would still have to have this on your paper. Now, if it was a calculator question, we'll do some more of those. We'll do some of those later in the week. If it was a calculator question, you could now go to menu, algebra, solve, and have it solve it, and you would write your answer. X equals, well, not your answer, but that'd be your solution to this, right? And then you go from there. So you wouldn't have any work to show because you would just solve it with the calculator. But we're going to do it by hand. This is going to be a no calculator. All right, so I've got to solve this. Now, off to the side here, I'll just mention that this is no different than having this problem right here. X to the fourth minus x to the third. What would you do to solve this? Factor out an x to the... Now, why didn't you factor out an x to the fourth? Because you can only do the one that they all have, right? They all have 3 x's. They don't all have 4 x's. In other words, you take the smallest one, the smallest amount of x's, and how many you could factor out. Well, that's the same thing over here. What's the smallest amount of x? Now, there's some other ways you could do this. You could put those negative powers down at the bottom. You could get common denominators. Of course, we didn't have very good luck doing common denominators on last quiz, so that's probably not the route we want to go. Okay? And to be honest, as we go forward, we're going to run into problems like this with fractions and negative powers. This is probably the best way to do it. Okay? So what we're going to do is we're going to look at our x powers. Which one's the smallest?
Negative 2.
Negative 2. So that's the one we factor out. Now you can factor out a 1/2 also if you wanted to, but that gets a little trickier. So I'm going to just factor out an x to the negative 2. Okay? Now, when you do that, let's talk about how you do it over here. When you factor out an x cubed from an x to the fourth, what do you end up with? X to the first. Now, you can think of this in 2 ways. It's x to the first because when you distribute back, you would add those powers, right? Or you can think about it as I had 4, and I took out 3. So it's 4 take away 3. Well, let's apply that same principle over here. I had negative 1/2 as a power, and I took out negative 2. So I had negative 1/2 as a power, and then I took out negative 2, which equals what? 3/2. So I end up with 1/2 x to the 3/2. Now, again, you can distribute it back. You would add the powers, and sure enough, negative 2 plus 1.5 does equal negative 1/2. So that's where it comes from. Plus, if I take out an x to the negative 2, I just have a 3. And then that equals 0. So we have to be able to do that factoring with negatives and with fractions. Okay, and what we do is we just take the smallest amount of x's we have. That's what we factor out. And then when we factor it out, all we do is subtract it from the power we have. Okay? Take this eraser right here. Erase that. All right. So nobody now is going to be watching what I'm doing. You're all going to watch him erase it. All right. So either it's tricky. Just tap. So this will move. Went to a whole new page. There you go. Tap. Okay. Hover. Get the click on the eraser. Click. Good. Make it a little bigger. Drag it over. Good. Okay. Erase. Just click. Get out of there. He's getting it. He's getting it. All right. Good. Now go back. That doesn't matter. You can leave the eraser. Very good. Now go back to Okay, now, one of these has to equal 0, right? So x to the negative 2, well, that's the same as this. When will that be 0? Now, you can't let x be 0, right? You can't have x in the bottom, but then again, look at our original problem. X not even in our domain anyway. X, in this function, x can't be negative, because you'd have square root of negative, and x can't be 0. Right, so we already know x has to be positive. Matter of fact, I should have wrote that down. They told us this, didn't they? They told us we're only looking from there to there, right? And now it makes sense why, because x can't be 0, x can't be negative anyway. So we're only looking from there to there. So when is a fraction ever equal to 0? If the top is 0. A fraction is only 0 if the top is 0 and the bottom is something other than 0, right? So a fraction is only 0 when the top is 0. Well, 1 is never going to be 0, so this will never be 0. So all we have to worry about is this. Now, this is harder algebra than you will have to do on Monday. It is not harder algebra, though, that you'll have to do subsequently in the future. This will come up, okay? So we subtract 3 from both sides. 1/2 x to the 3 halves equals negative 3. Multiply by 2, we get x to the 3 halves equals negative 6. Now, here, everything so far we should be able to do without a calculator, except now at this point. Now, if this was going to be a no calculator problem, this would be a negative 8 instead of a negative 6, because that'll work out nice. Okay. So what do we do at this point? Well, one way to do it is you can look at the 2 on the bottom as a root. So this is a square root, so we can square both sides. And then you got an x cubed. The 3 is a cube. You can cube root. So you can do it 2 steps. Or it's probably faster and neater just to multiply, or not multiply, but raise both sides to 2/3 power. Wouldn't that do it? Power and a power, you multiply, that'll just make x to the first now. So we just raise both sides to 2/3 power. So that'll be x to the first. And then this is negative 6 to the 2/3 power. Now, if that was negative 8, that'd be easier, because the third on the bottom is a cube root. The cube root of negative 8 is what? 2, negative 2, negative 2. And then squared would be 4. So that would be 4. Now, that's outside of our range anyway. Now, if you go to your calculator and check this one, it's 3.3 something, which again is outside of the range we want anyway. Okay, so let's back up here and now let's talk about a couple things. First of all, if this was a calculator problem, you wouldn't have had to have any of these steps in here, right? You would have had this, you would have had your derivative, you could have went to menu, algebra, solve, you could have solved it, and you'd have had this right here. And then, of course, we'd have thrown it out because it's not inside of our domain we're supposed to look in this problem. Okay, that's the first thing. Second thing is, go back, Richard. So we go back and we remind ourselves, what is it we were doing? Okay, we were doing what over here? Which one of these? Global max and min. And so all this works. See, sometimes, again, you get lost in all the algebra. We were trying to find what here? Look over there. We were trying to find what? The zeros of? Look, we were trying to find the stationary points, right? These are we were trying to find these places. We were trying to find possible largest values, right? Large and min values. We were trying to find those, okay? And there aren't any. There aren't any stationary points. So our only possible candidates are what? The endpoints, okay? Now, I could have done those in the beginning. You know, I was telling the other class, I mean, if you don't know what to do with this derivative, at the very least, you could have started your list of candidates. You could have said, well, I know I'm going to have to do f of 0.25, and I'm going to have to do f of 1, right? I'm going to have to plug my endpoints in, because those are possible max and min. And then any stationary points I have are candidates too.
Oh, sorry.
Oh, look at that. How did that happen?
Richard.
All right. Okay, so my list of candidates here, f of 0.25, so I got to plug this in where now?
Into the original.
Go back, Richard. When I start writing, make sure you go back to the other.
Original.
Listen, it is not going to work if you try to memorize, okay, on this one I do this, then do this. I mean, even if I print this as a PDF and you put it in your notes and you study and study and study, I mean, you can't memorize your way through this stuff, okay? You've got to think about why and what we're trying to find and why we're doing what we're doing, okay? The reason we did the derivative 0 here where the derivative equals 0, we look for stationary points because those are possible places where f might have a big or small value. The endpoints are also a place where f might have a big or small value. How do I get the values of f? I plug numbers into it, right? Into f. So, and look how I wrote it. I mean, geez, I wrote it f of 0.25, right? I know. So I plug it in, but she wasn't doing it. So I got to plug it into f. Okay? All right, go back. Yes.
So for the quiz on Monday, with the algebra that you done, is sufficient
No.
explanation
Well, right.
on no zeros in the.
Yeah, you would just say, you would just right here, you just, are we back? Yep, good job, Richard. We would just say no stationary points, right? We just go no stationary points. And the list of candidates is kind of your justification for a max and a min. Now, on the quiz on Monday, we'll stick with just basic factoring kinds of algebra. However, remember, on the quiz, we're also going to be learning about e to the x today. We're going to be learning about sine and cosine. There's going to be trig equations to solve too. Okay, so there's plenty of other stuff we got going on. All right, so now I got to plug these in. So 1/4, we can do this without a calculator. 1/4 square root is 1/2. And then 3 over 1/4, 12. 3 over 1/4 would be 12. 1/2 minus 12 would be negative 11.5. Okay? And then put a 1 in. Square root of 1 is 1. 3 over 1 is 3. 1 minus 3 is negative 2.
Are the mixed numbers okay there?
Mixed numbers fine, because what we're trying to do is what's the largest value. So right now we just want to know what the value is, so any number that makes sense would, to me 11.5 makes a lot more sense than 23 over 2, if I'm trying to compare numbers, right? So which one's my max? So my max value is negative 2. I don't care that it happened at 1 necessarily. Usually on max min values, they want to know what is the output, what is the value, and that's why we circle that. And this is the min. Now, isn't that interesting? It was only at the endpoint. So the left endpoint was the minimum, and the right endpoint was the maximum. Okay? Now, once we get better at this, later in the year, after Christmas, once we, I'm not going to say once we get rid of the riffraff. I'm not going to say that. And because I would be kidding. I'm just kidding. I'm just kidding. But you came in and smiled when you said you weren't going to be there. Okay. All right. So, no. But listen, as we get better at these problems, it might dawn on us. It wouldn't have now. But it might dawn on us that once we get here to f prime, and especially if it's some messy algebra, that we might just take a closer look at f prime. Remember when we did graphs earlier, right? And because we could see visually, we could see graphs. Well, look at f prime. If I rewrite f prime up there, it would look like this, right? That's what f prime would look like, right? Now let's investigate that just a little bit. This is f prime. And we're only talking about in between here, right, with positive x value. Now, what can you tell me about square root of x, its value? If you plug a positive into square root of x, is it going to be positive? So this fraction here is going to be positive all the time. What about this? X squared, isn't that always positive? This is positive plus a positive. So what we just said right there is that f prime, just looking at it, is always going to be positive. Chart, real quick. What's that mean if f prime is positive? F is always increasing. So what we have here is a graph that's always increasing. Where's its minimum? At the left endpoint, the max at the right. So we actually could have gotten away without doing any of that algebra. If we got to, you're gonna get fired. If we would have looked at f prime and realized that it was always positive, we could have said, hey, this graph's always increasing, so therefore the min is here, the max is there, we wouldn't need that other stuff. All right, so that's why I didn't let you have it. Yeah. Okay. So that's 25. Okay. Good job. Now, okay, now you're going to have to, now you're on page 4 and 6. Go back to page 4. All right, let's take a look at, yeah, I'll erase that later. Don't erase that. Okay. Now, what was the next one? Number 44 or 54, right? All right. Okay, let me make one quick comment about 44, and then we'll see if we can come back to it tomorrow or do a little more. It says that you have a cubic function, right? There's a cubic function, f. And it says, where does the slope have its largest value? Okay? Now, there's two ways to think about this. One would be harder, probably, for most of you to have come up with on your own, especially at this point. But maybe not. Just think about any graph. Where does it slope the steepest? At an inflection point, right? Where's the slope going to be biggest? It's chart stuff. That's going to be inflection point. So this problem is really about finding the inflection point. Now, to get into that a little more deeply, let's look at what a cubic can do, especially one with a negative coefficient. A negative leading coefficient means what? It goes which way first? Down, right? Now, there's three things it could do. And this actually gets into 46 a little bit. Go to page 6. Okay? There's three things this cubic could do. The most reasonable one you think about is that. Okay? There could be the one that flattens just for a second, or there could be one that just kind of is an S-curve and never does flatten. I mean, really, those are the only three things that cubic can do. Now, where is its slope the biggest value? Well, there's two types of big values. There's either positives that are the most positive, or negatives that are the least negative. Because these slopes, a lot of these slopes on the board up here are negative, aren't they? In this one, they're all negative. So what's going to be the largest one? The least negative, which does not happen there. That's where it's the least steep. Okay, here you've got a bunch of negative slopes and a zero slope. Which one's the largest? Zero. Here you have some negative slopes and some positive slopes, so the largest is the most positive, which again, so in all three cases, it happens at the inflection point. So if you think of that, then you're saying, oh, okay, go back to page 4. So if you think of that, then you're saying, oh, okay, this question is really just asking where's the inflection point. So you would do the second derivative, set it equal to 0, do a number line, and then see if it's an inflection point. Now, since it didn't ask for an inflection point, you really have to explain that that is the largest slope somewhere, okay? But now, I want to look at this a little different way that I hope going forward that you would think of. Let's think what that said again. It said find the largest slope of f. Well, what's the function that's the slope of f? F prime. So isn't it really asking for the max of f prime? That's what it's really asking for. It's asking for the max of f prime. Look at the chart. If f prime is the middle row, where do you look for a max of f prime? When f double prime is 0. Which is what we were just saying, right? Which is where we look for inflection points too. But see how that's the same thing. The max of f prime would be at an inflection point. And if we did that number line, if we did that second derivative number line, and it came out to be this, I think what happens when you do two derivatives and solve it, you get one, and you end up with this. Oh, nice try. My fault. I was too quick. Okay? If you do this, you do the second derivative number line, you get this. Well, isn't that a max? I mean, it depends what you're talking about. If this is your second derivative number line, this is an inflection point of f, right? Because it's going concave up to concave down. But if you're talking about f prime, this means f prime is increasing, then decreasing, which means it's a max, right? So two different ways to look at it, but it comes across the same. And we knew that back in chapter 1 when we looked at graphs. When we looked at the f prime graph, the maxes and mins of the f prime were the inflection points of f. Okay, so that's 44. 46 is kind of the same thing. They give you a cubic and they say, explain why, and I'm not too worried about part B on 46, They said, explain why it's either going to have, when it's a cubic, it's either going to have both a local max and a local min, or it's not going to have either. And you can just see it right here in these examples. Now, the better explanation would be to go into to go into the derivative of that 1 in 46, which is a quadratic. And what's a quadratic do? Well, there's three possibilities for what a quadratic could do. This is f prime now. Quadratic could do this, quadratic could do this, quadratic could do this. Now, in this case, now this is f prime now. What do we got here as far as maxes and mins? Of f. What do we got right there? Local max. What do we got right there? You gotta have both, right? You have to have local max and local min. What do we got at f right here? Flat spot, right? When f prime does this, it's positive, still positive. Flat spot. What do we got here? Nothing. We got this one, right? So we got two, local max and local min. We got flat spot. We got nothing, right? So that's what 46 was getting at. So those are very similar problems right there. Okay, let me, where's my, all right. Okay, go back to page 4. All right, so now we're looking at 54. Okay, 54 says you got a particle moving on the x-axis. Now this is the first time we've had a particle on the x-axis problem, but you're going to see a lot of them. Okay, and why are we going to see a lot of them? Well, it's like when we first did derivative. The very first thing we talked about when we learned about derivative and instantaneous rate of change was a car in Bismarck, North Dakota. Remember that? Okay, we go east of Bismarck, we go west of Bismarck. One's positive, one's negative, that kind of stuff. Okay. So if we're coming back towards Bismarck, that was a negative velocity, that kind of stuff. All right? Now, normally we don't put them in that kind of context. So, but what we want is we want to have direction. So we want to have both a positive and negative direction. Okay? So the easiest way to do that is just think of a number line on the floor here, like an x-axis. I mean, when they say a particle moving on the x-axis, think of it just like a number line. Okay? So what we got is 0 here in the middle, and I got 1, 2, 3, 4, and going that way I got my negatives, right? And so we got positions, kind of like east and west. Now, I put up on the board over here, okay, position, velocity, acceleration. We already talked about that, right? That's position, and the derivative of position is velocity, and the derivative of velocity is acceleration. So it's like p, p prime, p double prime. Position, velocity, acceleration. So think about the chart now. The chart, the 3 rows could be position, velocity, acceleration. So if my position is here at 0, and then I go this way, 1, 2, 3, what's my position doing? Increasing, right? Or what if I'm over here at -5? And then I go -4, -3, what's it doing? Increasing. So whenever I'm going to the right, my position is increasing. Go to the next row in the chart. What's the velocity? If position's increasing, velocity is positive. Now, I know in physics, how many are in physics, right? When you're moving to the right, velocity is positive. When you move to the left, velocity is negative. Well, here's why. Because of this idea right here. So when I'm moving to the right or left, I go from 5 to 4 to 3 to 2. My position is decreasing. So the slope of that, the derivative, is negative. Okay? So that's the kind of stuff, whenever you read a problem, position, a particle on the x-axis moving, that's what we're talking about. So its position is where it's at. Its velocity tells you which way it's moving. All right. So now read 54. Okay? Read it one more time. Just to yourself. Back to the next one. Or to 6. Okay, go back to page 4. All right, which one of these two are we doing here? It's a chart one, right? Because they want to know when is the particle going to its left. So what are they wanting us to really find out? The derivative of that is negative. That's what they're asking. And the way we find out when the derivative is negative is we do a number line. We've got a function that's our position function. We can't see the graph, but we've got an equation. The number line will tell us. Okay, so that's, okay, go back. So now, for number 54, they tell me that x of t, what is the function they give me? Okay, that is the position of the particle. Now, this is our first time we've seen a function called x. Right? I always say I don't like to use x and y, I want to use input and output. Well, here our input is t, or time, which, by the way, they tell us that the time is positive here. So, right, we start at 0 and then go forward in time. And then the output is x. Well, that's because we call this the x-axis down on the floor. So if I'm out here at 3, my position is 3. So at 1 second, maybe I'm at 3. So my input is 1, the time, and my output is my x coordinate, okay, on the x-axis. So x is the output, actually, in this problem. So the velocity would be x prime. So I want us to use that notation. I don't want you to write velocity. I want you to write x prime, okay? But that's what we're talking about is velocity. So this question is really about what Nick just said. This question is really about when is x prime negative. That's the key. You've got to be able to read a question like this and understand that that's what they want you to find out. They want you to find out if x prime is negative. So once you know that, then you're like, oh, okay, that's a number line thing. That's first I find out, if I want to find out when x prime is negative, I first find out when it's what? 0. Right? I first find out when it's 0, then I check in between. If I know when it's 0, all the other places it has to be positive or negative. Okay? So what's x prime? 15t to the 4th.
Minus 75t squared plus 60.
Thank you. Equals 0. Very good. That's a point. Without the equal 0, we don't get the point. Okay? That's our velocity. We want to know when that's 0. This is easier algebra than number 25, right? So what do? Take out a 15. T to the 4th minus okay? And then factor some more. T squared minus 4 and t squared minus 1, which factor some more. T plus 2, t minus 2, t plus 1, t minus 1. So we get t equals and those points are what? Yeah, they're zeros, but I mean, what do we call them? Those are stationary points. See, good. The other class. The candidates. Right? We're not doing candidates. I mean, they could be candidates. They could be candidates if we were doing a global maximum. We're not. We'll talk about how this could be a global maximum problem in a minute. Now, talk about this particle moving back and forth. What did the 1 and 2 mean? I know. Yeah, the slope. I mean, this particle's moving. Let's don't use the word slope. Stop moving. Where it turns around. To turn around, it's got to stop. Several people might have said it. I don't know. I've heard a lot of things. 1 and 2 are when it stopped. Now, we want to know when it was going left. But before you can know when it was going left, you got to know when it stopped. Because if it was going right, we got to know when it started going left. Well, it had to stop to turn around to go back to the left. So that's why we set it equal to 0. To find out when it was stopped. Okay? All right, those are stationary points. What do I do next? Number line. I was about to write f prime. That's no good. That was not very smart. That's x prime. It's an x prime number line this time because our function is x. Okay? So 1 and 2 we put on the number line. And we can put 0, we can put 1.5, we can put 3. Remember, this is all no calculator, so we're going to plug these in without a calculator. So we start looking at it, we got to plug it into x prime. But geez, I got 4 different versions of x prime here. And you're plugging in without a calculator. Which line? 1, 2, 3, or 4? Really? I would not want to plug a 1.5 in there to the 4th power. I don't like that. I would put it in 3. Now 4 wouldn't be bad either. 4 wouldn't be bad either. But remember, all we care about is whether this is a positive or a negative. I don't really need to know the exact value. I just need to know if it's positive or negative. 15 is always positive, so that's not going to have any effect on when I multiply, right? So right here, if I put a 0 in, this will be easy. Well, 0 would be easy to put in with a positive. Yeah, so that'd be easy. So that's positive. But if I put it here, 0 minus 4, that's negative. 0 minus 1, that's negative. Negative times negative is positive. So that's positive. So 1.5. Now 1.5 squared, you might not know what it is, but it's certainly got to be less than 2, doesn't it? Or excuse me, less than 4. It's less than 2 squared. So that's going to be negative. And 1.5 squared's got to be more than 1. So that's got to be positive. So negative times positive is negative. We had 3, it'd be 9 minus 4, that's positive. 9 minus 1, that's positive. So all positives make that. Now you might be thinking at this point, because every number line we've done has done this, it always alternates positive, negative. Not true. We said that 1 and 2 are where it stopped. What if those were all positive? What would this particle be doing?
Touching the zero.
It's stopping and
Stopping.
Okay, yeah, now everything you guys said are right. It'd be flat spots if we were doing graphs. It'd be just touching if we were looking at an F prime graph. But for this particle, what it's doing is going right, and then at 1 it stops, keeps going right, stops again at 2 seconds, and then keeps going right again. But if it was going to go back to the left, it would have to do it at one of those points, at 1 or 2. Well, it turns out it does it between 1 and 2. So when I looked at people's number 54, very few people had all this stuff. Now, again, it's the first time you've seen one of those, so I didn't really expect you did, unless the couple people I helped this morning didn't spread it around the room, which might have happened too. But you know what I'm saying? So that's fine. But going forward, as we do these local max-min problems, these chart problems, these global max-min, understand that when I come around, this is what I got to see. I mean, this is what gets graded on the thing. If this was a calculator problem, you just wouldn't have had these lines in here, right? You wouldn't have had those lines. You know, you would have written this down still. You'd have still set the derivative equal to 0. You'd have went to your menu algebra solve. You'd have solved it. You'd have written down the 1 and 2 that the calculator gave you. You'd have done your number line and all that. And then you would say, for your final answer, you can't just leave it like that. You got to say, okay, the particle is moving left between 1 and 2 because at that point the velocity x prime is negative. That would be a really good answer right there. You would finish it up by saying that.
I recall you mentioned that the AP test graders told not to look at the number line. You just have to substitute all those values in and then redo the.
No, they were told to just ignore the number line as a justification. They don't care if you have the number line. So that last part I just said would be the key.
As long as you come to the conclusion that it goes 1 and 2.
That's right. So you say, yeah, so you've got the number line. As far as them looking and seeing the negative, I'll be honest, I never ignored it. I would look at those things, but they give a point for the justification, right? 1 to 2 is your answer. You get another point for a proper justification. So this is not get you that justification point. You have to say the particle is moving left between 1 and 2 because that's where x prime is negative. And then you get that point. So that's what I was saying. Okay? So just writing that out and communicating what the chart is telling you is where you get that information. All right. I feel like I'm leaving something out, but I don't think so. So we've got a very important stretch run here. So let's stand up. 45 seconds. I'll give you 45 seconds. So yeah, I'm going to give you 45 today. Okay? 45.
Sure I stood up so fast on my clothes.
Yellows. Is that right?
She's been guiding about it all day. Are you saying like a nice black? Yeah, exactly. Whoa. They didn't wake up at 7. Yeah.
All right, here we go. Have a seat. Thank you. Now, turn to page 147. 147. Okay, page 147. Now, section 2. We're skipping section 2.5 because it's a section on what's called differential equations, and it's kind of separate from what we're doing here. So we'll talk about tomorrow, and it's going to come along for the ride the rest of the week, and there's going to be part of that that's going to be on the quiz. Okay, it's stuff that we kind of periodically do as we go throughout the year, as it fits with what we're talking about at that time. So we're going to skip 2.5 right now. We're going to go into 2.6 and 2.7, which fit with the stuff that is right here, this idea of global max min and so forth. Okay? Now, another thing I said that was important that we have to know for this particular quiz is these derivative rules. So we're going to add to those here just quickly, and then we're going to do an example problem with what's going on. So we already have, of course, our power rule. So let's just add a couple of derivative rules in here that we already know. For example, we already know e to the x, the derivative is e to the x. It's its own derivative. And we already know that the derivative of sine x is cosine x, right? We already know those derivative rules. So what we have to do now, and then we also know about if you have a 2 multiplied on the inside, what do you do with it? You got to kick it out, right? If you've got a 3 multiplied by the x on the inside, we got to kick it out, right? We know that. But if you have just an x minus 1 or something like that, that just stays in there, stays on the inside. If you have a 4 on the outside, it just kind of hangs out. If you've got 4 sine x, the derivative is, you've got 4 sine x, the derivative is 4 cosine x, right? The 4 just, if it's on the outside, it just kind of hangs out there and stays. Like if you had 2x cubed. The 2 would stay there, you bring the 3 down in front, right, and be 6. So you got a number on the outside, it just kind of hangs out and stays there. So we already know some of those kind of basic things, and we keep practicing those. All right, but what we have to do is we have to learn about what if you have a different power, or excuse me, what if you have a different base than e? What if you have 2 to the x? Well, because of time, I really would like to show you this the long way. Remember the f of x plus h and all that? I'd really like to go through that, show you that on the calculator stuff. It's kind of cool how it all works out. We'll come back to that another time. But for right now, for time, I'm just going to tell you that that derivative is 2 to the x. Oops, bad mistake. 2 to the x times ln 2. 2 to the x times ln 2. Now, why is there an ln 2 there? Okay? The quick version of y is this right here. Don't write it down or anything, but e to the x, remember, is its own derivative, right? What's that mean? It means for every y value you get on e to the x, that's also the slope, right? That's why it's its own derivative. Whatever its y value is also its slope. Well, that's e to the x. 2 to the x is not as steep as e to the x. So when it has that same y value, what's its slope? Not as much. Smaller. By how much? Well, what's ln 2? Somebody got their calculator real handy? Just do ln 2. Yeah, I just need a decimal. 0.693. How much smaller is this slope than the e to the x slope? It's smaller by a factor of 0.693. So that ln 2, so it's kind of cool how that works, because if this was 3 to the x, the derivative is 3 to the x ln 3. Now what's ln 3? It's 3 to the x, e to the x, or 3 to the x is actually steeper than e to the x. 1.09. 1.09. So this one is steeper by a factor of 1.09 or whatever you said. Okay? So ln, now, does that fit with e to the x? What would we have tacked on there? ln e. What's ln e? 1. So it does fit with the rule we said there. So the rule actually looks like this. The derivative of a to the x is a to the x times ln a, whatever the base is. We just have to, you just have to memorize But I said earlier, you can't memorize your way through the stuff with the derivative rules, you just gotta memorize. Okay, and you'll have some practice problems on those today, on the homework here. Now, I know the temptation is whenever you have 2 to the x, you want to bring that x down in front. It's not a power rule. Power rule is only when you have x raised to a number. Here we have a number raised to an x. That's an exponential function. And it has to fit this rule here. Okay? A couple of quick comments. If you have 3 raised to the x minus 7, what's that derivative? 3 to the x minus 7. No. ln3. It's just ln of the base. It's just ln of the base. The x minus 7 just shifts everything to the right. Remember how we always said leave the inside alone? Leave the inside alone when you do the derivative. X minus 7 is the inside. Just leave it alone. Okay? What if this would have been 3 to the 2x? 3 to the 2x. ln3. Isn't that where we have to kick out a 2? When you multiply a number on the inside, you have to kick it out. Same rule we've been talking about with these other functions. So we have to kick out a 2. We cannot take that 2 times that 3 and make 6, however. Because this 3 is raised to a power, and this one is not. Okay, so we cannot put those together. So we just leave it just like that. So 3 to the 2x, the derivative is 3 to the 2x with an ln3 kicked out, and then we have the other rule about a 2 on the inside, we have to kick out a 2. So there's going to be some of those kind of practice kinds of things today. Okay? Another one that we don't have yet. Natural log. What's the derivative of a log? Because this is what section 2.6 is about, is e and logs, or exponentials and logs. The derivative of ln x, without going into y or anything, is simply 1 over x. The derivative of ln x is simply 1 over x. So what if you had ln of x minus 7? Let's make that 2x minus 7. 1 over 2x minus 7, and then kick out a 2. And usually we put that 2 on top. Usually we put that 2 on top. Okay, but that's what it would be. So it's 1 over 2x minus 7, and then kick out a 2. Okay, what about another base? What about some log with a different base? We'll just call it a. Well, it's going to be very similar. It's going to be 1 over x, but then just like we had to do with exponentials, we have to tack on, except instead of tacking on an ln a, we tack on a 1 over ln a, which should be easier to remember because the derivative itself is 1 over x. So we tack on a 1 over ln a. So if that's log base 2, we tack on a 1 over ln 2. If it was a log base 7, we would tack on a 1 over ln 7. But it's still 1 over x, so it's still the same thing. Now, does that make sense? Yeah, because this would be 1 over ln e. And ln e is just 1. So those are our rules for logs and exponentials, along with our various combinations that we have. All right, and then the only other one I have to give you, where we talked about the derivative of sine was cosine. What's the derivative of cosine? Not quite. Close. Close. Think about cosine. Cosine starts at 0, slope, right? Of course, sine starts at 0, so that's good, right? Outward. But the slopes of cosine start by being what?
Small.
When they small and no.
Getting smaller.
More
Negative. Negative. They go down. The cosine graph goes down, right? So the slopes are negative and get more negative. So the derivative of it's got to start at 0 and go down. The sine graph starts at 0 and goes up. So what do you think it is? Instead of sine, it's negative sine. It's negative sine. So the derivative of cosine is negative sine x. So you just got to memorize that. The derivative of sine is cosine. That's the first one we learned. So that should be easy to remember. Derivative of sine is cosine. The derivative of cosine is negative sine. All right. So that is it for those rules. That's all we should need for those rules. All right. Now, look. Oh, man. Sprint to the finish. Not really a sprint. How we can get it. We got just enough time. We're going to look at number 37 on page 147. I think I already told you to go there, right? Page 147? All right. Now, this problem is a doozy. I mean, this problem has, well, just read it. Read the directions for number 37. Okay? Which one of these are we doing here on that one?
Second one.
Both. It asks for the global extremes, but it also asks for local max min, and it doesn't ask for inflection points.
Yeah.
That's all chart stuff. Local max min, inflection points, and then global max min too. It wants both. Well, that's not all bad because they both start out the same, right? Which is what? Do the derivative and set it equal to 0, right? For the chart stuff, we'll do a number line. And for the global max min, when we do the derivative set equals 0, those will be our candidates, right? So it's really doing both. Now, I'm not going to ever give you a problem where in one problem you do all that, okay? We'll split it out and just have you do parts of it and so forth. But this will be good practice to try to tie all this together. Plus, it's got trig in it, so we'll be able to talk about that, okay? And now, hopefully, we have a little more ammunition here to go to the homework and be productive with, okay? Now, so to start the problem, I do what? Derivative. That'd be 1/2 plus cosine x equals 0. Perfect. And they also did tell us that we're limited from here to here, which of course are endpoints where it would be two of our candidates, right? Oh. Yeah, that was me. Fire, yeah, that was me. Sorry. All right, so, new page. All right, so, we've got this equals 0. So now what? Solve it. So cosine x equals -1/2. So now I could write arc cosine, whatever, we don't have to. We can just say, where does cosine equal -1/2? Which quadrants?
Second and third.
Second and third. Where's now? Some of you may have to write down some of this stuff, so that's fine. Cast, right? Cosine is going to be negative over in the second third. -1/2. If you remember, if you memorize these the way Mrs. Payne did them, the triangles would look like this. This would be Miss Clark 2, yeah. Root 3 over 2. Yes. So cosine is -1/2. But I also said, if you remembered it, if you learned it maybe this way, SOHCAHTOA, adjacent, -1 over hypotenuse would be cosine. This would be root 3. Either way you did it, what angle's there? 45 be root 2 over 2. It's 30 is the small angle. It's across from the big, the small angle's across from the smaller number. This is 30 up here. This is 60. It's pi thirds. Pi thirds, okay? Remember, 1/2 is smaller than root 3 over 2. Root 3 over 2 is like 0.7 something, 0.786. Okay? The smaller angle is across from the smaller side. Okay? So this is 60, which would be pi thirds reference. Well, what is that then? 2 pi over 3, 4 pi over 3, right? Pi is out here at 3 pi over 3. So we're one short of that, be 2 pi over 3, and one past that, be 4 pi over 3. There will be, on our next quiz, a no calculator problem with trig where you're going to have to be able to do. And I'll just tell you right now, 6 days away to get that figured out. So, and we're only going from 0 to 2 pi. So what do we call those? 2 pi thirds and 4 pi thirds?
Yeah.
Those are our stationary points. Right? That's where this unknown graph that we're looking at here flattens out. Right? Might be a local max, might be a local min, might be a flat spot, it might be a global max and min, right? Those are going to be candidates. Right now, matter of fact, I could just off to the side here, Now, rarely do we have a problem that has both the number line and the global max min stuff in it, but I could start my list of candidates, right? My endpoints are 0, 2 pi, my stationary points are 2 pi thirds, and 4 pi thirds, right? So that's my list of candidates, and I want to see what outputs F has at those points, to see what's the greatest output and what's the smallest output. So that's my global max min side of things. I've done the derivative, set it equal to 0, found the stationary points, I had my endpoints, there's my list of candidates, all I have to do is do that work there. I'll save that for a little bit later. So now let's say we're doing the chart stuff. So here's where local max mins could be. I do what next? Do a number line. An F prime number line. So 2 pi thirds, 4 pi thirds. Right? And then what? The numbers in between. 0 would be a good one. Pi would be a good one. 2 pi would be good. And I plug those into, right, over here on my list of candidates, I'm plugging back into the original because I want to know where F, the original, has its greatest value and its littlest value. Okay? But over here, I'm talking about F prime. So I put 0 into that F prime right there. What's cosine of 0? Cosine of 0, I need my unit circled on. Cosine of 0 is? It's the x value. Wait, why am I at pi over 2? Okay, you guys are talking me into stuff. Cosine of 0, and I'm talking about what's the cosine at 0, right? An angle of 0. Right? I just plugged the 0 into there. I didn't say where is cosine 0. That's what you were thinking.
Sorry.
If I say where is cosine 0, that's at pi over 2. What I'm doing here is cosine of 0. So I need 0, which is right here. And what's the cosine? It's 1. It's 1. See, this is, I'll be honest, I like graphs better. What's cosine of 0? Right? At 0, cosine has an output of 1. Okay, so cosine of 0 is 1. 1 plus 1/2 is 1.5, but all I care that it's pi. Okay, then what am I going to put in? Pi. What's cosine of pi?
-1.
Pi, that's over here, right? Cosine's -1. Pi, that's down here on the cosine graph. -1. Okay, -1 plus 1/2, still negative. Okay, 2 pi, back around to here.
Same thing.
Cosine's 1 again. 1 plus 1.5, positive. Now, that tells me a lot of stuff, that number line, right? Tells me what? F, don't say it. F is increasing till there, then decreasing, then increasing. So it's increasing, decreasing. So what do I have at 2 pi thirds? Local max. Stationary point, we already knew that though, right? The local max. Because this goes from positive to negative. Now remember yesterday how I said you had to write that out? So in your answer to this question, you would have to now say, and they actually wanted both sets of coordinates, which we'll get into here, we plug it back to the original, but normally we would just want, where is the local max? So you would write local max at x equals 2 pi thirds, local max at x equals 2 pi thirds, because f prime,
0.
no, because f prime changes from positive to negative, therefore, f changes from increasing to decreasing. See, the number line is there, and that's great, but you've got to communicate the information it's telling you. The local max is at 2 pi thirds because f prime changes from positive to negative, so f goes increasing to decreasing. It's a local max. Local min at x equals 4 pi thirds because f prime changes from negative to positive, so f changes from decreasing to increasing. You've got to say that for local min and local max. Okay? So that answers part of what they wanted. They wanted local min, they wanted local max. They also wanted global min and max. So let's go do that right now. That was our list of candidates, where the derivative is 0, which was our stationary points, and at the endpoint. So we're going to plug those into our original function f. This gets a little bit messy here, but it's not bad. Put a 0 in here. That's easy. 0, sine of 0, 0. So that's just 0. 2 pi, well, what's 1/2 times 2 pi? Pi. Plus sine of 2 pi. Sine of 2 pi is back to here at 0, so that's just pi, which we know is about 3.14, because I'm trying to find what's the largest value, right? What's the smallest value. So at 2 pi, I have an output of pi. What about 2 pi thirds? So that gets a little tricky. I got 1/2 times 2 pi thirds. So that's pi over 3. Now what's pi over 3? That's about 1, right? Pi is about 3.14, so that's about 1. Plus, what's sine of 2 pi thirds? I still have my triangles up here. Sine of 2 pi thirds is root 3 over 2. So we can do that. Pi over 3 is about 1. Root 3 is about 1.7 or 1.8 divided by 2, so it's about 0.7. Well, it's actually 0.78 something, I think. So we got 1 plus about 0.7, so this is about 1.7. Roughly, that's about all we need. We just want to know what's the largest and smallest value. 4 pi thirds, let's see, what's 1/2 times 4 pi thirds? That'd be 2 pi thirds. Now 2 pi is about 6 divided by 3, so that's about 2. Okay, and then plus, what's sine of 4 pi thirds? That's still on our picture here. Negative root 3 over 2. So this would be about, what, 6 divided by 3? This was about 2, and then this was about 0.7. So 2 minus 0.7, that's about 1.3. So that's good enough. So our largest value is here, and our smallest value is there, right? But that list of candidates is justification. Those are the only places the greatest and smallest values could be. And so we just found what they were. Okay? All right, I think we're almost there. What else did the directions want that we haven't done? I'm not going to worry about the graph. Inflection point. Where do we look for inflection point? F double prime. We want an F double prime number line. Right? Chart stuff. Well, go back to F prime, which is up here. So F double prime was negative sine x equals 0. Of course, divide by negative, and it's just where sine is 0. Well, here's unit circle. Where is sine 0? And at 0, too, right? 0 pi and 2 pi. Now, little piece of information here. Whenever we do local max, local min, or inflection points, we are not going to consider the endpoints. And the reason for that is simply because we got to look on both sides, right? To have a local max, we got to see it change from one to the other. To have an inflection point, we got to see F double prime change on both sides. Well, if we're at an endpoint, we're not looking on the other side of the endpoint. So we are just not going to consider, the endpoints as possible inflection points. So we will throw those out. Okay? So the only possible inflection point then, the only pip, is going to be pi. Okay? So we do our number line, F double prime. We put pi on there. Now I need to pick something on either side to plug into F double prime. What would be something to the left of pi? Wait, why not 0? Okay? Most people will say, oh, let's put in 0, and let's put in 2 pi. So then you go up here to put in 0, and what's sine of 0? No, sine of 0? 0. Oh, wait, we were hoping to get a positive or negative. Why did we get 0? Oh, because that was one of our zeros, right? We threw it out because it's an endpoint. So I don't want to put a 0 here because I'm looking for something that's positive or negative. If people get confused, they go to put in 0 and they get 0, and like, wait a minute, that shouldn't happen. Well, it's because you picked one of these up here. So you do have to put something like pi halves and 3 pi halves. Okay, here we go, we're almost there. So at pi halves, we're gonna plug that back where? This is an F double prime number line we're looking at. We want to know if F double prime is positive or negative, because that tells us if F is concave up or concave down. We're plugging this into F double prime. So pi halves, we plug it right here. What's sine of pi halves?
1.
Right here, sine of pi halves is 1, right? With a negative is negative 1. Okay, 3 pi halves, sine of 3 pi halves, negative 1 with a negative positive 1. So is that an inflection point? Now we would need to write this out. We would say inflection point at x equals pi, since F double prime changes from negative to positive, F changes from concave down to concave up. So x equals pi is an inflection point. That's a big problem. I mean, that's got it all. I mean, that's got everything on that other worksheet. It's got global max min with our list of candidates. It's got the number line for F prime and how we use that. And it's got the number line for F double prime to get inflection points. That's every single thing that's in the chart is there. So if you can do that one, you got it made. Okay, now it doesn't mean the algebra or the trig part might not get a little tricky, or plugging in the values might not, or whatever. But that's an important one. So throughout the next several days, every assignment, every day will have a problem or two like that. You need to get better. I will post some videos, not only of today's lesson, but I've got a separate video that's just a trig, no calculator, local max min problem like that, or an inflection point problem, or I don't think I have a calculator one on there. I might, but I've got some of those that are up there where I just go through one of those problems. Okay, that's going to be a big part of the points on this next quiz that we do. Okay, major emphasis. All right, so for your homework. Now, let me make one other comment here. That next line after 2.4, it's got 2.6 and 2.7. Okay, those two lines that are together there. All right, now remember, 2.6 was the exponential section. All right, 2.6 was exponentials. Now, let me ask you something here. Here's an exponential graph. Here's a natural log graph. Do those have a lot of chart stuff in them? Local max, local min, inflection points. They're not very interesting from the chart perspective. So you're not going to have very many problems in section 2.6 that are about the chart and this kind of thing. Mostly what you're going to have in these sections is derivative practice with those rules that we learned. Okay? Now when you do those derivatives, they give you f is a function and they say find f prime. And so you just follow the rules and do it. And then there's another one where they say, okay, take that same problem and then do the second derivative. And then there's another problem where they say, okay, take that same function, do the antiderivative. So you're practicing with that. And that's what the homework does. Now, it'll also say in the directions to check your graphs for reasonableness or check your functions by graphing them to see if they're reasonable. Don't worry about doing that. Don't mess with that. Just here's your function, do the derivative, follow the rules. Do the next second derivative, follow the rules. You know, just do that part, but don't do the thing with graph. Okay, then when you do the section 2.7, there will be some questions practicing the derivative rules with sine and cosine. But then there will also be, that's the section that'll have a problem. Like, for example, well, I don't think even yet today I assigned one quite as big as number 37 that we just did there. But you get some practice with the derivatives, and then there'll be some local max min stuff. Okay? All right, then we'll go over that a little more tomorrow, and hopefully have a little bit more work time tomorrow, although we do have a short day going, so probably about an hour. We got to talk about those differential equations we'll do tomorrow. Thursday then will be questions, a little more work time. Friday will be probably even more work time for practice, ask questions, you know, those kind of things. But we should be really getting the hang of it by then and only have minor issues, you know, by the end of the week. If you have major issues, we need to be getting those taken care of early.
Okay, so if you had like so if we went on in that problem and had like an F triple prime or something like that, so with that negative sign, would that be like a negative cosine then?
Yes.
Okay.
Yeah, and that negative there is just like a 1 in front, negative 1 in front, and any number that's out in front of a function just stays there. So the negative one would just stay there and the derivative sign would be cosine, so it's negative cosine.
Okay.
Is there another question?
So was it 2.6 and
2.6, and yeah, those two that are together right there below 2.4. 2.6 and 2.7. Okay? And then basically Wednesday will be the next group, and then Thursday will be the next group, and then Friday will be the next group, and quiz on Monday is kind of where we're headed. Yes, ma'am. What's that?
Talk louder, is it?
That's fine. Yeah, that's fine. So as long as, if you look at cosine x equals -1/2, and can look at the unit circle and realize that there's two factors, both of them. Yeah, I mean, a lot of times I draw a triangle just so I have cosine of the x, and so that's really. So, yeah, I mean, everything's over. I basically have to be able to know cosine x equals -1/2. Two factors.
Oh, they're not that chill anymore. So I thought they said, hey, we want to. Or they did it.
Yes. Even, yeah, the E, like 16 to 30, even, the E is what that means, yes.
So since there's demonstrate, when do you want the
They did quick and light.
Of course. I'm not planning, so.
You're not doing this.
I might have to.
Mr. Clark,
Yes.
let me psych myself out. On 37, just as an example, when you have your f prime and it's 1/2 plus cosine x,
Right,
and then you go to your f double prime and you
Right.
have your negative sine x,
right.
wouldn't that 1/2 be 1? So it's-
No.
Why?
If,
Because wouldn't it be 1/2 and then you take your 1 down in front?
no, that's
1
no,
minus 1
because
is
1/2 is just a constant, first of all, so that would be that. What's the slope of the constant? Just 0. So the derivative is 0, but then it's, what it really is not 1/2 to the 1, it's 1/2 x to the 0, that's what it is. And you bring the 0 down in front, and that's what makes it 0. So anytime you're doing the derivative of just a lone constant,
Then it's 0. Alright, I was just messing with myself.
Yep. No, that's easy to do.
I will be gone.
Gone tomorrow. Okay. So we'll be, plan is probably to that next group, well, on that side sheet said the solving equations worksheet, which we already did. And then to that next group of problems, and I'll have it.
So they're black lines. And so like it's